We don't even know ourselves.
Alright, so in SAS Enterprise Guide, so I'm going to be very truthful with you. Actually, no. Well, I mean, I'm always truthful with you. Let me ask you a question first. So I'm going to open the data for this assignment. I'm going to open the data for this assignment. So this was car values for A7. So did you always have size small, size family, size up?
Yeah.
Nice. No. Yes? No. Yes? No.
I didn't.
Yes? No?
I would say no.
Yes? No. See, this is where I'm having some fun. So here's the deal. When I posted this data set, I didn't think these variables existed.
Yeah, it was.
And this is the truth part. I actually did not run the analysis. I know. I knew how to run it. I assumed it was going to work. I mean, I didn't make my answer key before I posted, and I didn't remember these being here. So, and this is why I'm really asking. When you guys had opened your assignments to begin with, did you see it?
Yes.
How many say yes? How many say no? Okay.
Mine's right here and not there.
Well, it's okay. That's my question.
Like I saved it, it is not
Like
there.
you saved it somewhere else,
Yes.
and it's not there.
Yes.
Okay. So somebody saying over my data set. Maybe, maybe not. If you trust them.
It's not me,
Like
because
it's
I don't know how
just
to use
supposed to be
computers.
We need to work on that. So somewhere, somehow, and
No, that wasn't very
I speculated this at one other point this semester, but it wasn't as obvious as this. So, thank you. The next time I do this, I will be very specific with the students about not... And it's not like you can just hit save. Like, you actually have to export it. Export it into... So whoever did this, I mean, put a little bit of effort into it. And I don't know if they're trying to be nice. I don't know, thank you.
I'll take it.
And there are, but there's... Well, it's, you know, I teach 3 classes. So it could be any, you know, it could be not necessarily in this class. Okay, great. So, fun times.
This data set actually confused me for the quiz. That it has to be 2 variables, but it's 3. So what's the correct answer now?
Right. So this is wrong.
Yeah.
Okay. Well, let's take a step back.
K minus 1.
Let's take a step back. This is not wrong. Okay. So the data set, it's accurate to create a size small car with 1s for the small sedans and 0s for everything else. 1s for the families, 1s for the others. So the variables themselves, as data, are not wrong. Okay?
You just have to choose the right one.
So for the assignment, yes, you would want to make sure that you choose the correct ones. Okay. You cannot put all 3 into your model and get a correct answer. But theoretically, the data as it stands is not incorrect. So if you did use this, that was the other thing I was afraid of, like whoever did this didn't do it.
Right. What's that predictor?
Well, and so this is also where I think people are adding things to my data set. Stop it! And if my Saturday students are listening, stop it! Yeah, we'll blame that. I mean, because this predictor, I mean, whoever did it, 55, this predictor, actually typed in the things for the assignment. So, I mean, they kind of, sort of, maybe helped a little bit, but not really. So, yeah.
Because I can see at the top where it was like one record wasn't running. I was like,
See, and this is the issue. So yeah, so if you had the original data and saved it to your data file,
save over.
which great, do that. Next time I'll make sure I tell everybody not to save over my data.
One is this is also wrong. 54 is also wrong. Is it?
I don't really know what 54 is, what 1 plus is. I don't know if it used to actually be a correct input for a car name, and somebody typed over it, which is what I'm guessing happened. Is that they just edited that variable, and like, you know how you can go in and right-click and say, add a new row. So, this is fun. It shouldn't impact any of the results. It shouldn't.
So even if, like, because on mine, I even have that predictor thing.
Oh, you do?
Yeah.
Okay. So somebody might have gotten in and did the predictor thing first.
Yeah.
Before somebody else added.
So even having that is probably fine.
Yeah, so having a predictor one's not going to be a big issue because it doesn't have a value score.
Okay.
So it's never been included in the model. That's your one missing. That's your one missing right there.
Okay. I follow.
So look, we're learning all the things. So one of the things we're learning, where my PowerPoint goes. So interpretation dummy variables. The other questions we have is data. Changes?
I want that predictor to throw off some of your summary.
It could throw off your summary statistics, yes.
Okay.
But since you really didn't have to do any summary statistics, well, yeah, you did for like the part 1.
Yeah.
Yeah, but I'm with Sam. I think the predictor was in the original equation. Or, well, I guess it just depends on, it depends on who was the first person in, basically. So, as long as it's not going to throw it off enough, because they're mostly like average values. And if people's answers are slightly off from mine, then I know what's happening now. Okay, so now that we've figured out that issue, good times. Now let's do what I actually wanted to do. And it actually works out well that somebody has done this. So what I wanted to do first, so your assignment is actually asking you about family and upscale, right? Those are the two variables they want you to use. So if we went into analyze and we did a regression analysis, and we did a linear regression, and we're using value score as our dependent variable, and we were using the family and the upscale sedans as our explanatory variables. Our model, we're going to use the full model. I'm not going to worry about any of the statistics. To make life easier, I'm going to get rid of the diagnostic plots for now. And then I'm going to run this. And so I'm going to get a result, and I can make an equation. So my estimated regression equation is a a y-intercept of 1 point. Let's go 2 decimal places. 1.46 plus 0.0003 for my family sedan minus 0.27 for my upscale sedan. Here we have upscale sedan as being a significant variable, family sedan not being significant, which you can kind of tell by the slopes there. So I'm going to leave it up to you whether you keep it in the model or don't keep it in the model. But here, as far as interpreting things, we would say if, I'm going to start backwards. And we'll start, so let's do this one. So if a small car, then the value is 1.46. So I put 0 in for family, 0 in for upscale. If it's a small car, then the value is 1.46. If a family car, then the value is 1.46 plus 0.0003. So it's actually 1.4603. Kind of weird. If upscale, then the value is 1.46 minus 0.27. So what do we end up with there? What?
1.9.
Yes.
So is it incorrect to say, like, if the sedan type was upscale, the value score will decrease, or should I say that in the detail?
No, you can say, well, I would say it would decrease by 0.27. So you could add in that extra piece. Because it's a difference in, it's decreasing by a teeny tiny bit, or it's decreasing by a lot. So go ahead and make the magnitude of it. Yes.
At some point in PowerPoint, in your slides, Father, I can find every number, that instead of saying is small in value, or like in the circumstance where it's small, because a W variable that doesn't have a value, you say it doesn't change, the value doesn't change.
Yes.
You can also say that.
Yes. So if I'm talking about, like especially like in the context of multiple regression, if it is a small car, then the value doesn't change, right? So here I'm just trying to be specific because of what I have in mind for the next couple of things. But you could just say, if it's a small car, then the value doesn't change. If it's a family sedan, then it increases by 0.003, and if it's upscale, then it decreases by 0.27. So that interpretation would be good. Or here I'm just actually giving you like the raw values because we're going to compare them in a second. Yes. Yes.
The way I wrote this equation for that for the assignment where it only asks about these two is this is the equation in relation to the small sedans.
Yes.
This makes sense here. But when we use for other questions where you had to include this as well as other factors,
yes,
then I don't know how to write. But I still write in respect to small sedan. And what if there is more than one categorical variable? In respect to what? We have to mention the control variable every time we write the equation.
You do not have to mention it every time you do the equation. So the only reason you need to have it is just so somebody knows if it's 0, 0, then what is your control condition. So at some point, you want to have like a list of kind of like types of car are family sedan, small, and upscale. So as long as you have that somewhere, then anybody who has your equation can go back and reference and say, okay, if I put in a 0 for family and a 0 for upscale, what do I have left? Oh, it's a small car. Yeah.
Why do we have to include the variable that is not significant in the equation? Like for family sedan?
Yes. So, answer is twofold. Number one, I've got a thing in mind that I'm doing, so kind of educational purpose. Number two, it's an all or nothing game, right? So if you want to keep upscale sedan in your model, you have to keep family sedan as well. If you get rid of upscale sedan, or if you get rid of family sedan, you have to get rid of upscale sedan as well. Because the variable is size of car. So you can either have the size of the car in your model, or you can not have the size of your car in your model, but you can't pick and choose which size of cars. So for here, because I like and I think having the size of car is really important, this is what I did. And so this is having family sedan and upscale sedan in my model. But here's my next question. If I went and modified my text, we're still all talking about dummy variables. If I decided, let's make upscale sedan my control group. So I'm going to leave upscale sedan. Oh no, but upscale sedan is going to be my control group. So I'm going to take out upscale sedan, and I'm going to add the small sedan. So not your assignment. This is now going into, what is it? Professor Mullins likes to say, hey, watch this. This is just going into, hey, let's check this out and see what happens. So I'm going to run this analysis. In this case, I'm going to, let's not replace the results. All right. So now I have a new equation that you can't see. So now I have a new.
He's just freaking out.
I love this. Not like I need to use this at all. All right. So my new equation, I've got y hat. And I'm going to use the intercept, which is 1.19 plus. Oh, this is fun. 0.27 for the small sedan, plus 0.27 for family sedan. So if my car is small, it just takes about 3 or 4 minutes and then it'll fix itself. You need to look away. Look away. Maybe that's a little strobe light effect. So if the car is small, then my value is going to be 1.19 plus 0.27, which just happens to be, is it right? 1.46. If we have a family, then my value is 1.19 plus 0.27, which is 1.463. And if we went out a few more decimal places, we could probably get to, say, 1.4603. And then if my car is upscale, then my value is just 1.19. So does it matter which way you do it? Which 2 of the 3 dummy variables you include? It doesn't matter. So it doesn't matter which 2 of the 3. You can't include all 3.
What happens if you do that?
I love that you asked that question. Let's find out. So hold on. So let me, before we do that, there we go. Let's snip this real quick. What happens if we do all 3? I'm pretty sure things blow up, but we already had the screen blow up, so we're good. Modify the tabs. As we have small, we have family, let's add in upscale. You get this note right here. So it's still kind of sort of gives you an equation, but it really doesn't. Right, so down here you have your slope, and then you get to the upscale sedan, and it's like, no, like, this is 0. Right, so it says the model is not a full rank. The least square solutions for the parameters are not unique. So the math and the matrix algebra that you have to do to make this work isn't going to work. It kind of explodes. Kind of like how you're not supposed to divide by 0. It's not exactly what's happening, but it's kind of similar. So you don't have this full rank matrix to actually be able to do everything on. And so whichever variable you put in last, it's going to, by default, assume that that is the control and put it as 0 down at the bottom. This also happens. So Sam, does that answer your question?
Yeah, I guess one more follow-up question. If there was another variable in that equation, like the predicted reliability or something, would you still interpret the control dummy variable the same way? Okay.
Let's do one. Okay, let's just do it. Yes, but no. So that's
fair.
Big picture, yes. So let's say we added, and actually we'll go back and modify the task. We're going to kick out small, so it fits kind of. We're going to add in, let's add in price. Run this with price. Yes, we don't like those last results. Alright. Let's not do price, because that is. Let's do something that's meaningful. That's bad. Cost per mile? Sure.
Yeah.
Be like, yes, that one. Let's make something meaningful out of this. Ah, great, cost per mile. So, regression equation. Y hat is 2.7 minus 2.4. And this is X cost plus 0.28 X for the family sedan plus 0.28 X for upscale sedan. So interpretation stays the same, right? So when you're talking about multiple regression, when you're talking about interpreting the slopes, holding everything else constant, then you interpret, right? So you can't, like, if you actually wanted to predict something, you would have to put in a value for cost, right? But as far as interpreting the individual variable, you say holding cost constant, then family car is going to increase your overall by 0.28.
What about for small?
So for small, then it would be for a given cost value. It does not, small cars do not change the predicted value.
Do they holding all of their values constant? Small cars do not change.
Yeah, you can do it that way too. So either holding all of the values, either holding all others constant, or given a specific cost, it doesn't change. Either one of those wording is totally fine. Since there's only one variable, I could say given a specific cost, doesn't matter if it's small or not. If I had multiple variables, then I would stick with probably holding all the other things constant. What other questions do we have with the freebie screen? Let's see if I get out of this at the next one. And I feel like there's like a wire I should jiggle or something. Isn't that how you fix things? Yeah.
Maybe if you turn it off the back.
Yeah, nothing?
Have you tried?
How about you guys? Try this.
Dang it.
Let's save this so we're good there. Other questions that maybe don't need sass? Other questions. What other questions do you have about regression at this point? None.
About the multi-collinearity, when do we check that?
When do you check it?
Yeah. How?
And how? And how? Yes.
And a follow-up to that, how much collinearity that actually matters, and what is our cutoff? Is it completely our choice, or is there any standard?
So there is actually a standard for multicollinearity, and it's a correlation of 0.7 or a variance inflation factor above 10. We haven't talked about variance inflation factors yet. That's something we can possibly talk about today. That was part of the extension piece. So we're going to take it while we got it going. So multicollinearity. So generally, as you would start out doing a regression equation, or a regression modeling project, if I'm going to do multiple regression, and at this time, you guys are awesome, but I'm not going to do your assignment for you. We'll pick a different data set. So we pick a new data set. Let's have some fun. And I'm going to pick this data set because I know it has multicollinearity issues. And I don't know if ours does or not. So if you want to follow along, in our big shared data sets, I'm going to pick the fitness data set. And so in this fitness data set, we have the name of a person, we've got their gender. They went on a run, we know how long it took them to go on that run. We have their age, their weight. I'm going to think their weight is probably not in pounds. Throw it out there. Probably in kilograms on that one.
That's
Totally pounds? Yeah, 68-pound, 42-year-old. We have their oxygen consumption. We have their pulse when they're running. We have their pulse when they're resting. We have the max pulse they reached. And then we have a performance index. These are the data points that we have, the variables that we have. So the first thing, if I wanted to model, I would look through there and figure out, well, what is the thing that I'm interested in, right? What's my dependent variable? What's the thing I want to measure? And to make life easy, I'm just going to tell you what it is. So for this assignment, for this piece, the oxygen consumption is the thing that I want to try to predict, the thing I want to try to explain. So given all these other things that we know about a person, how can we predict their oxygen consumption? Okay. And then we have to decide, well, what variables do we want to put in? Since I don't know a lot about any of these, maybe I want to put all of them in. They all seem like they're good things that could, maybe not their name. For convenience sake, I'm going to leave out their gender, just because it's not already a 0-1. If it was a 0-1, I'd probably throw gender in there too. But right now, for convenience sake for this, we're going to leave it off. So all of these other variables, though, I think are fair game. So options that you have to look for multicollinearity. The first thing you can do is you can analyze and you can look at multivariate, and you can just look at the correlations between all of these variables. So for multicollinearity, am I interested in the independent variable and the dependent variable? Just the correlation between independent and dependent? Just the correlation between the independent variables? What is the idea behind multicollinearity?
Just the independent.
Just the independent. Okay. I think I have sound. Let's just do this. Multicollinearity. Just the independent. Come back to this. So if I'm doing multivariate analysis, I can find the correlation. My analysis variables are just going to be runtime, age, weight, basically everything except, so from runtime all the way to performance, except the oxygen consumption, because I don't have to worry about it. So I'm going to drag all of these over as the analysis variables. This is one option of multilinearity. Run this analysis, create the correlations. Then I have a fun little correlation table. So the values that you're going to see for the correlations you only have to worry about 1/2 of your correlation matrix. The top value is your R. The value under this is your p-value. So we never talked about this, but we can decide if we actually have a significant correlation or not. So we could actually run a hypothesis test asking, do we have a correlation that's 0 and there's no correlation? Or is there some type of correlation? And there's a p-value to decide, is it a statistically significant correlation or not? So in this case, using our alpha level of 0.05, the correlation between age and runtime has a p-value of 0.29. So there's not a statistically significant correlation between age and runtime. But if we go over here to performance, there is a statistically significant correlation between runtime and performance. As far as multicollinearity goes, if the absolute value, we throw the absolute value because it doesn't matter if it's positive or negative, is greater than 0.7, we're going to say that these are candidates, these are something we need to watch out for. So the runtime and performance has an issue. Their runtime and performance. Age and performance has an issue. Looks like weight and performance are okay. Run, rest, pulse, those look to be okay. What else is kind of, oh, here. Looks like weight. No, run pulse and max pulse seem to be correlated. And so all I'm doing is just looking through here to find correlations that are bigger than 0.7. So it looks like performance and runtime, performance and age, and max pulse and their running pulse seem to be really highly correlated. Okay. So this is one way to kind of decide, is there some multicollinearity? So there's collinearity between two of the variables, but we have a lot of variables in our model. So even if there's some collinearity, maybe that's okay. Right? Performance is correlated with 2 out of the 7 variables. So you have to decide, is that collinearity between those 2 variables worth taking it out of your model? So it's a little bit of, here's a cutoff. You get to choose based on what you know about the subject and using that kind of as support. A different option.
And you would take it out of your model because, like, essentially, because it's so correlated with 2 other variables, you'd be explaining whatever variance that has on the dependent variable with those other 2 variables. Is that
right? So the idea would be that I couldn't decide. So the point of our regression model at this point is to try to explain what's going on with the dependent variable. And so if I don't know if it's coming from runtime or if it's coming from performance, then how do I explain what's happening, right? There's some relationship between runtime and performance, and so maybe it's runtime that's really doing the influencing, maybe it's performance that's really doing the influence, I don't know which, because they're too correlated to them. Yes?
So how do you do that in a category?
Can't. Right, so here comes the question of how do you do that with a categorical variable? And so the multicollinearity really is mostly between continuous variables and continuous variables. That's the only way you're going to be able to use the R, the Pearson's R, because that's the only correlation value. It has to have continuous variables and continuous variables. So maybe there's another metric that we could use, and this is kind of the extension to it. And so the reason I say this is an extension, like this is the stuff that I learned a third of the way through my PhD, like full-time regression class. Okay, so be aware of it, but we're not going to dig into it too bad. But we have software, and it'll calculate these values for us, so why not use it? So if we were actually going to create a regression equation using all of these variables, I've decided kind of eyeballing it, nothing's just really so correlated that I want to throw it out of my model. So I'm going to create a regression. So I'm going to go back to my fitness data. Delete. I'm going to analyze. I'm going to do a regression analysis. So in my regression analysis, I'm using oxygen consumption as my dependent variable. I'm using everything else except oxygen consumption as my explanatory variables. I'm leaving my model as it is. In my statistics, we've said, hey, let's not deal with this at all. But in my statistics, there's a diagnostic over here, and it's called the variance inflation value, the VIF. If you click that little button, everything else gets to stay the same. This time I may have fun. I may actually go add in a scatter plot with a regression line for fun. We're going to run this. And it took a little bit of time. And the reason it was taking a little bit of time is what it was doing was actually calculating this extra variance inflation factor. And so what we have is when you have this variable in your model, one of the things we're going to talk about today. So. For fun, one second. How many of you guys have been having fun doing going through the SAS tutorials? Anybody? SAS tutorial? Anybody?
Are they chronologically organized? Or?
Pretty close.
Okay.
So, for fun, if you get bored or if you just really want to know what to do, descriptive statistics, hypothesis testing, regression. So here, when I say I'm going to do 9B, I think. It's actually a pretty cool little read. If you get sick, close your eyes real quick. Hold on, it's kind of huge. So if you get sick, close your eyes real quick. This one's actually really a fun one. But we're going to go down. Collinearity. Look, whole section on it. So, in our fitness data set, runtime and oxygen actually have a strong linear relationship. We didn't look at it with the dependent variable. Runtime and performance are linearly related. We already kind of figured that out. And so what's happening here, this is actually kind of like the visual thing of what's going on with the collinearity. We're not going to get to that. So this is basically what we're doing right now. So as we do this, diagnostics, here we go. The variance inflation factor provides a measure of the magnitude of the collinearity. This is what I was actually trying to get to. So the variance inflation factor is a relative measure of increase in the variance because of collinearity. So we're looking at 1 over 1 minus that r squared. And so really we're calculating the variance inflation factor for each term in the model. And so as we're doing this, we're kind of looking at so here, this is actually the output we have on our screen. What we're looking at is if we find a variance inflation factor that is greater than 10, then that's going to say there is some strong collinearity between these variables. Right? And so runtime, age, and performance, those were the three that kind of stuck out in the past. They're the three that stick out here. So if we were going to get rid of and remove one of these variables from our model, which one would we remove? Performance, right? So it has this really high variance inflation factor. But really, so what it's looking at is it's actually calculating if we have this in the model versus if we don't have this in the model, how does it change our r squared? Right? That's kind of the formula that you've seen. So it's 1 over 1 minus that r squared value, and you're doing that sub I, so you're doing it for each and every variable. So what is the, I don't want to say proportional change, but that's kind of what it is. When you're considering having this variable in your model or not in your model. If we get a score above 10, then that's something that we can get rid of from our model. So if we go back to our regression equation. So we have a really high significant regression equation. So our r squared, we have a statistically significant model. Our adjusted r squared is about 0.8. But if we went and modified our test and took out performance, and what we actually know that I didn't tell you is performance is actually a calculated column based on some of the other variables in the model. Okay. So there is a collinearity issue. Not here. And if we run this again, we still have a statistically significant model. Our r squared is still 0.8, but now we've gotten, look at all the variance inflation factors. Once we remove performance, we got rid of most of that collinearity. Our model still predicts, still explains, but now we can feel more confident in our results. Yes?
So the way we go about it is remove that with the highest variance indicator and then redo it till nothing is about it.
That is one way that you can create your equation, yes. So one of the things, and I haven't really focused on this a lot, but we talked about the idea of a best model, right? Not the best model. So what we're doing is we're creating an equation given our data that we think explains what's happening. Right? We want to make sure that we have the highest, or the lowest p-value we can get, the highest adjusted r squared, the fewest variables. We don't want multicollinearity. We want to take out outliers if they're really influential. Those kind of things. So we do all this stuff to get a regression equation, and we're like, we think this is a good one. But then what do you do once you create that regression equation?
Predict.
You can predict things. And people use the predictions. And they make forecasts. And they plan based on this regression equation, I think it's pretty good, but may not be the best, but I think it's pretty good. And so this is one of the things when it comes to regression. People use regression all the time, and it's a great method to try to do prediction. But it also has its drawbacks. Because if I add one more data point, that can change my entire equation. If I take out one outlier, that can change my entire equation. Okay. So based on your data, based on you try to get the best equation you can, but there's other ways to do prediction besides linear regression. And if you have a lot of data, join me next summer or next semester, and I'll tell you. There's a lot of other ways you can do prediction as well, right? So regression used to be kind of our gold standard because we had to do things by hand. And you can do the matrix algebra by hand, and you can make it work, and you can handle all sorts of things. Half of you guys are going, a third of you guys are going to go take a class that's totally devoted to regression. You guys have taken like econometrics already. You've had a class that your entire semester you did regression. Lots of good things. Depending on your situation, you'll learn little bits and different pieces as you go. Other questions about regression at this point? Yes.
So about the residual clause, when are we going to examine, or in other words, is it going to be a criteria to determine whether this model is good or not? It will just be used to evaluate how accurate the model is.
So, let's say for your assignment. So right now, I don't focus a lot on checking model assumptions. That's what the residual analysis does. It's all about the model assumptions. It's all about, are the variances equally distributed? Are they not? Are the error terms normally distributed? We look at the residuals. We try not to find a pattern. Fun story. Where we go? If you look at the SAS stuff, and you really want to know, there's an entire regression assumptions. There's actually 2. Alright, you can read all about them. And it gives you much more detail. For me, as long as you pop up that residual plot, look and make sure that there's no pattern that's really showing up, that's all I'm really looking for my assignments. Right? Because if there's no pattern, and actually, hold on, I think this one does it well. Again, close your eyes if you get sick. So verifying your assumptions. So looking at your residual plots, right? So if you're looking at your residuals by your predicted values, this is kind of what you're looking for. And it really does most of the stuff. So here, this first model, a little bigger for you. This is what you're looking for. So your residuals by your predicted values, there's no pattern, and that's a good thing. If you wind up with a pattern, right, then you don't have the right, it's not a linear regression, right? This is like a curvilinear, right? We messed up. If you've got this kind of look going on, right, remember that cone-shaped thing we kind of talked about? Then your variances aren't consistent. There's something kind of going crazy. And then this one is, this is actually our observations aren't independent, but there's something going on. There's a pattern. And for me, as long as you look at a residual plot and kind of notice that there's no pattern, that's the check mark that I'm looking for. Okay.
So if we notice that there's a pattern, what do we write?
That there's a pattern, and we need to go back and look at this. I'm not wanting you like. So you could go back and try to figure out, oh, there is a pattern, and it's curvilinear, and then you could go on and you could run a curvilinear model, and you can do other things. But for us right now, if there is a violation, we're just noting that there's a violation, and then moving on. Yes.
So I have a question back about A7.
A7.
So if we have a regression equation and like there's not a car size variable in there, is the y-intercept still going to be for the small?
No.
Okay.
Because if you've taken out family sedan and upscale sedan, you've taken out small car too.
Okay.
So there's nothing in it. And it's all or nothing. Good question.
What does the force residual plot tell us?
This one?
Yeah.
It tells you that they're not independent. It's, again, this is one of our advanced topics. It's a thing called autocorrelation. And generally what this will be is like if you have some kind of time series data, you may see something that looks like this. So the data points aren't independent. There's some other variable that's kind of influencing them, and in this case it's probably like season or something like that. But yeah, if your big point is, and if you go on it actually tells you 1, 2, 3, 4. A possible solution is to use regression analysis with an autoregressive error task. So there are fixes for most of these things. In some cases you can, so like here where our variances aren't consistent, you could actually try to transform a variable and try to fix it. So there are fixes for these things, but that's just kind of above and beyond what I want to teach in this class. Yes.
You're using residual plots for finding out.
You can, yes, absolutely use residual plots to find outliers. Oh look, detecting outliers. Man, it's like this sassy G thing. It's like all prepped and ready for answering questions. I was starting to make slides last night. I was pulling all the information off here, and I'm like, nope, I'm just going to use this. So in your slide deck, there is a link to this. So for your residual plots, the big thing you're going to use for finding outliers is, it gets a little long. There we go. It really is going to get here in a second. Plots. Alright, so you've got your residual plots, you've got your residuals by predicted value plots. So the residuals by predicted values, that's the one that's going to tell you is there a pattern or not. The residual plot down here is what we're interested in now. And what it'll do look at there. Is we're looking at this residual, and this is going to be our standardized residuals. And so anything that's not it at all, just take that back. That one is not it. Keep going. There we go. Any outliers? Diagnosis. Here we go. I wasn't down far enough. So the two things that I like, I use the student residuals and the Cook's D are the two things that I use for finding outliers. The first thing with the studentized residual, and this is the one we talked about in class, is if you have that studentized residual and it's above 2 or above 3, depending on how many observations you have, that's kind of what you're looking at to find some outliers. So we'll come back to Cook's D in a second. So if you're looking at a picture, so it'll say R student right here. And when it says R student versus your predicted value, then anything above or below 2, so above 2, below -2, these are what you can look at for your outliers. And there's actually some code, so you can most of the time hover over it and see like what the name is. Or there's actually some code that will tell you what these outliers are. And that's right up here. So it'll tell you how to do it. Again, above and beyond what you have to do. But yes.
So for our assignment, is this a plot that we should include if there's that one part at the very end?
All I'm really looking for your assignment is to say I check for outliers.
Okay.
There weren't any crazy outliers.
Is that this? Or
Yes.
Is that, okay.
Yeah, so if you want to provide support that you check for outliers, you can look at this plot right here, which is your R student by your predicted value. And so anything above 2 or below -2, you can consider those as outliers, and you can go investigate what they are. Or we also have this, it's called a Cook's D. And this is one of those when you see the diagnostic plots. Right? So here's your Cook's D. These are also, anything above your line right here can be considered an outlier. So those are your two potential outliers.
You're not wanting us to like then go and remove the outliers.
But then we don't need to change our equation.
Just say, hey, we look, here's a couple.
However, I think you guys have been doing this, which is why it's taking you so long. Like you guys are digging into all the things.
There's so much you can do.
There is so much you can do. And I think that was, and I thought last time when I posted A7, I thought I made my expectations clear. And then you guys got into it, and you just forgot everything that I said about making it easy. And you're like, oh, I gotta do all this. Because there are, and that's the thing. When you get into regression, there are so many things, right? We haven't even talked about the idea of, so we have these outliers, right? So in this case, I'm going to go back here so we can actually use names. Right, so in this case, this posterior here, this is Gracie. And if we were over here, Gracie's way up here, she's the one that they're considering the most influential. So Sammy and Jack are outliers. But Gracie is actually what we're calling an influential outlier. Okay, so that's what the Cook's D does. It actually shows off the influential outliers. What the do you guys know what I mean when I say influential outlier?
Which impacts the slope.
Yeah, it's actually going to change the slope, right? So if I take out Sammy, my slope's not going to change that much. If I take out Jack, my slope's not going to change that much. But if I wind up taking out Gracie, it actually is going to have a significant impact on the slope of my line. Okay.
But Gracie's not an outlier.
So there's the fun part, right? So when you're looking at our student and you're using the +2 -2 rule, then Gracie doesn't look like she's an outlier. If you look at Cook's D, then Gracie looks like an outlier. There are many, many ways to try and find an outlier.
And what's the actual like regression equation for this? What are all the variables that are going into this?
Yes. It's all.
Is it all of the variables?
It's all but one. I think we're going to
okay.
one.
Okay.
But it's the majority.
So it's right. Okay.
Yeah. So it's
running out
runtime,
all
it's
of
the
this.
pulse, it's the
Yeah. Okay.
So at this point, and this is where like the more you know, the more you can get into things. And it sounds like you guys have been like learning a lot on your own. Without even using the SAS guys to tell you what to do. And now everybody's like, oh. And that's kind of the way it is with regression, right? So like in college algebra, you learn how to do a simple regression, right? We kicked it up a notch to multiple regression. We kicked it up, we started using categorical variables, now we're doing dummy coding and stuff. You can start to get into the outliers, and the idea of, is it an outlier, is it not an outlier? If it is an outlier, so let's talk about Sammy. Sammy's an outlier, for whatever reason. What do we do with Sammy? We kick Sammy out of our model? Do we leave Sammy in our model? A lot of the times, right, if our goal is explanation, maybe we want to kick Sammy out of our model. If our goal is prediction, maybe we want to keep Sammy in our model. What's your purpose? What are we trying to make this equation? What are we trying to do with it? What about Gracie? Gracie's actually influencing my model. Did I get rid of her? But she doesn't meet the outlier criteria using our studentized range. So is she really an outlier? How do you decide what is an outlier? See why I didn't really go into all of this. So when it comes to making a regression equation, there are a lot of factors to consider. Subject matter is huge. Knowing your data is a big deal, right? So is it a big deal that I get rid of Sammy? Maybe it is, maybe it isn't, right? Let's go investigate Sammy. So we investigate Sammy, we find out that he's really old, and that's why he's an outlier. Alright, well, how important is age in our model? Age isn't really that important in our model. So maybe we did Sammy okay. Age is really important in our model. Maybe we should get rid of Sammy and see what happens. So there's all sorts of conditions, and you can tweak and play and try to find the best model for your data. But then when you use new data, then what? What does that do to your model? And so that's why I'm not a huge proponent. And again, I think of regression more in a prediction set than I do in an explanation set. So if you're trying to explain the data that we have, then getting rid of outliers can start to make sense. If you're trying to make predictions, then keeping outliers in will make more sense. Okay, so what's your goal? What are you trying to do? Who's your audience? What story are we trying to tell? What is this model going to be used for? These are all the kind of considerations that you have to make when doing a regression equation. For you guys, you don't get to get into that deep. Know the ideas of simple regression, be able to translate into multiple regression, use some categorical variables, look at the residuals and make sure that nothing looks funky, and I'm happy for you. Yes?
So then, can you go back to how you look for correlations with capital interest?
So the problem with looking for multicollinearity with categorical variables is that it's really more of a case-by-case analysis than just like a nice sled, here, let me look at things, right? So when you're looking at correlation, not correlation, like multicollinearity, it's more the idea that, I think Harry brought it up a couple of classes ago, like let's say all of the high values are red cards and all of the low values are white cards, right? So it's more like a systematic sampling thing as opposed to a multicollinearity thing. So it's not that those things are correlated with each other, right, in the true sense of the word correlated. Now there may be a relationship between them, and it's something that we may want to know, and that's why it's important to know your data, right? So if you do the descriptive statistics of your data to begin with, that may be something that you notice. And then you'll have to decide, well, what do I do with that? Do I need to sample again? Is this just a trend that I'm going to have to worry about? If that's the case, do I need to have a different regression equation for red cards and a different regression equation for white cards? Which could be a possibility. Should I not have color of my car in this model? Yeah, we'll maybe not explain as much of the variability, but I know this is an issue with this variable. It's not a good variable to have in my model. Those are the kind of considerations. So there's not like a nice, easy push button above 0.7 kind of answer. Yes.
So to give a very specific example, for the prior schools, there is one thing called income range of the parents' income as well as the economic situation of the children. So both of them would be categorical.
Okay.
So if we do a multicollinearity between them, we could probably say if it's one for both for a long time. So that would probably be a way to choose whether or not to choose both or only one.
I would probably go with, this is where the subject matter expertise would come in, because you're looking at things from two, so like when you're looking at the parental income, right, the parental income can range from $0 to $100,000. But when you're looking at, and you could actually, even though it's kind of categorical, you could still treat that as a continuous variable, because it linearly makes sense to do so, right? The people making 10,000 is definitely less than the people making 100,000. Whereas the socioeconomics piece is going to be they're disadvantaged or they're not. So it's that 1 and 0 thing. So what you could do is look, so several things. One thing, there is actually a correlation that you can do. It's called the Spearman correlation. So here we've been doing the Pearson correlation. Pearson is continuous to continuous. There's a Spearman correlation that'll actually let you do categorical to continuous. So that thing that does exist, right? Again, above our pay grade in this class. But that thing does exist, right? So you could do that and see, are these two things correlated? Here I would probably do this, like if you're thinking like maybe these are, I would probably do descriptive statistics and really see, okay, so it looks like all of our disadvantaged kids, their parents fit in this section. And all of our advantaged kids, their parents fit in this section. And if that's the case, then let me just use one variable or the other. So it's just kind of thinking through what would happen and how could you use it. Yes.
So in real life scenarios, how often does the regression equations change? Because as you said, new data keeps coming in.
So ideally, you would come up with a model that would become fairly static. That being said, it depends on your business, right? And what you're actually trying to predict. So if I'm trying to forecast, for a year in advance, I want to have a fairly stable model, right? Because I don't want it fluctuating a whole lot. Like I want to be fairly confident in my year outs. And I'll take variables into account that will help me do that. Now, if I'm trying to, I don't know that you actually use a regression model to predict the stock market, but if you would, right, that's something that's changing minute by minute. So then that regression model could be changing nanosecond by nanosecond, right? So it kind of depends on what your goal is. So if I'm looking at purchasing, then I've, based on the past 5 years of sales, here's what purchases have been. I've got a pretty stable model as I go along. Every quarter, every year, I'll update it. But if I'm, a small store, nah. I'm a bigger store, I'm doing more and more things, I've got people who are updating these equations all the time. And then you start to kind of figure out, well, as I update them, how much is really changing, what's really changing, is it making an impact or not? Again, small data, you can do one thing. Big data, we would do something different. And then we'll actually find the best models to make those predictions. It's a little bit of an extension. Talked about some things. What do we have? Let me talk about 2 more concepts. So, other things we can do. We've been talking about simple linear regression. We've talked about multiple linear regression. We could have things that don't fit into a straight line. When they don't fit into a straight line, we can still create an equation. Now my equation curves. But now we'll have a variable, x1, and then we have a second variable that's x squared. So it's the same variable, but we've squared it. And it just goes into our equation, and we find out, is adding that curvilinear piece significant or not? So you can do it just like it's an extra variable, just like it's kind of like a dummy variable. Again, not kind of where we're going, but it's there and yes, you can do it. You can also add an interaction term, where you combine 2 variables. So we have variable 1 all by itself, variable 2 all by itself, and we can see if there's an interaction between variable 1 and variable 2. It's similar to kind of like an ANOVA, right? The factorial ANOVA that we did. In fact, I kind of told you this a little bit before, we can actually use multiple regression and ANOVA really kind of go hand in hand. Alright, so you've seen the ANOVA table as we're doing our regression analysis. When you take experimental design, you can write model equations. When you see these model equations, when we have just a mean, and then we have one variable that we're interested in, that's kind of our completely randomized design. Here we have our blocking design. We've added another feature. Here we have an interaction. But these alphas and betas are still those correlation coefficients that we've been talking about. So I'm not going to show you the math in between. But there's math that will let you go from regression to ANOVA and ANOVA back to regression. Another thing we haven't really talked about, but we could, is you can always transform variables. Okay, so let's say a variable, well, let's do this one, right? So we're going through our analysis. We have this regression equation. We like it. It's great. It's predicted. It's got so that high or low p-value, high r-square. We've just got a couple of variables. I decide to go check my assumptions. When I check it, I find out that I've got that funnel-looking thing going on in my residuals. Right? So I have a non-consistent, a non-constant variance. One of the ways you can fix that, so right now I just said, hey, note it, and you're good to go. But a way that you can fix that is by using a transformation. So you can go in and find the variable that's kind of causing your issue and do some math on it. Okay, basically, you're creating a new variable. It's just transformed. So instead of looking like 1, 2, 3, now it looks like 0.7, 0.8, 0.9. Okay, so changed it a little bit. The log function is one of our favorites. I take log transformations of variables. And basically what it does is it'll change the scale of the variable. And it'll put it into perspective. So instead of some crazy big number, take the log transformation and kind of shrink it down a little bit. And that's one of the ways that we could fix that non-constant variable problem. The only bad thing is when you transform variables, then when you're doing your interpretation, you gotta remember to transform them back so that makes sense. So, last thing you need to know, we'll take a break. There is that logistic regression thing. If you go to SASE G10, it tells you all that you want to know about logistic regression. So if you guys are going to use a logistic regression supporting your final project, A, talk to me, and B, if you need some help, there's a whole tutorial. Big key differences between linear regression and logistic regression. What's the big key number one difference?
Type of dependent variable.
The type of dependent variable. Okay, this right here. What's that? That one right there is probably the biggest difference between linear and logistic regression. So far, all we've been doing is predicting continuous variables. And we can use either a continuous or a categorical variable to do that. But if we want to try to predict a categorical variable, that's where logistic regression comes in. So you have binary logistic regression, when you just have a 1 and 0, that's like your traditional logistic regression. You can go up to ordinal logistic regression. Ordinal logistic regression is used a lot in education. When I try to predict letter grades, right? So I want to try to predict, are you going to get an A, B, or a C? So not just a pass-fail, but are you going to get the A or are you going to get the C? So the independent variables stay the same. You can use continuous or categorical. The dependent variables change. The equation changes. Right? So you have the equation of a line for our linear regression. You get this logistic. So do you guys know what a logistic line looks like, or a logistic curve looks like? It's kind of like a little S. So this would be the equation. So you're still using your betas. In fact, this right here looks exactly like this piece right here. Right, so we actually take part of the linear equation. It fits into our logistic equation. In fact, that's kind of what we're doing. There's some transformation there. For linear regression, we're focusing on slope and the y-intercept to do our explanation. In logistic regression, we focus on the odds. Okay, you focus more on probabilities of things happening. The hypotheses look very similar. So as far as in terms of using the parameters, they're identical. The thing that changes is the interpretation, right? Is there a linear relationship? Is there a logistic relationship? But the concept stays exactly the same. A whole bunch of videos, there's tutorials, it's all you want to know if you want to know more about spirit. Let's do this. Let's take a break.